Hello and welcome to this webinar, Tips and Techniques to Simplify MOSFET or MOSCAP Device Characterization. My name is Jim Busey. I am an Applications Engineer here at Tektronix for the Keithley Parameter Analyzer product line. Today, I'm going to start out with some simple tips and tricks for making better semiconductor measurements focusing on DC or IV and CV measurements. I will then switch focus to touch on more specific applications and finally go over how you can leverage Keithley equipment to simplify performing required measurements for your applications. Every day, you as engineers and researchers are challenged to create a new or improve an existing technology or process. Whether you are designing a low-power front end for the next generation cell phone or researching materials for high-efficiency solar panels, electrical measurements are a fact of your day-to-day activities. And I think we all know that testing inefficiently can seriously hamper the work you are trying to get done. This is why making smart measurements is very important. Many times, while testing our designs, we run into many more problems regarding measurements. Whether the measurements do not match exactly what is expected, or if they're completely off the wall, think about negative resistances or capacitances on the order of farads, it can be very difficult to troubleshoot the cause. The unexpected measurement can have many causes. Some common mistakes are cabling mistakes, such as disconnected or reversed cabling, high leakage or excess impedance in the cables without any hardware or software compensation for that impedance. The device could be blown out, broken, or not working correctly for some reason. The software can be configured incorrectly. Measurement hardware could be broken, or the software could have a bug. Or finally, the results could be correct and the device is behaving differently than you expected it to. Looking at a modern measurement system, we can see that it is quite complicated. Everything I mentioned on the last slide can be seen here visually. In order to take the measurement of our device, the software has to talk through the controller over the chosen bus to each individual instrument. Those instruments must accept those commands, interpret them, and make a measurement of the device through cabling and a test fixture or prober, and return that data back over the bus to the controller. When the data makes it back, usually there is some kind of post-processing in the software layer before it sends the data, and usually a graph, back to you, the user. Now, when there's an unexpected measurement, the easiest way to narrow down where the error lies is to be sure that as many parts of this system are working correctly as possible. Throughout the rest of this presentation, I'll be going through the steps you can take near the device end to confirm that your measurements are correct. This includes connecting cabling as well as performing compensations for sources of noise and leakage in the system and more. I'm going to start with a few basics of low-level DC measurements. The simplest technique to reduce error in a DC voltage measurement is to use a 4-wire setup. The goal here is to eliminate the effect of stray impedance in the cabling. The fact is that all cables have an impedance, and that a current through that impedance will cause a non-zero voltage drop over the cable that can lead us to believing there is more voltage across the device under test than there actually is. This becomes extremely apparent when measuring very low resistances or when sourcing high currents. The solution to get rid of this unwanted voltage drop is to take the voltage measurement closer to the device under test. This way, we're bypassing the cabling that is causing the problem. Note that we do have impedance on the cables connecting to the voltmeter, but we do not care about it because as far as we're concerned, there is no current running through these cables. Therefore, there is no voltage drop across them. This allows us to measure voltage accurately and can give us good resistance measurements even down to the micro-ohms. For high resistance or high voltage measurements, we need to take cable leakage into consideration. Inside of a coaxial cable, we have a rather large but finite impedance between the conductor and the shield. Because the shields should be held at 0 volts, there exists a voltage across this impedance when we source voltage. This results in a leakage current which cannot be compensated for using 4-wire measurements. By sourcing a guard voltage on an inner shield, we move the leakage current from between source and shield to between guard and shield. This current does not matter because we are making measurements on the source and not on the guard, and therefore does not affect our measurements. On this slide, I have real-world examples of the two solutions I just spoke on. In the first example, I was attempting to measure the resistance of a 0.1 ohm resistor. I tried both 2-wire and 4-wire configurations. Calculations from the 2-wire measurement reported 2 ohms, while the 4-wire measurement reported 0.11 ohms, which is much, much closer to the correct resistance value. At very low resistances, cables can contribute greatly and skew your measurements. For the guarding example, I performed the same measurements on a rubber band, which apparently has a resistance of around 550 gigaohms. When unguarded measurements were taken, however, enough current leaked through my BNC cable that the measured resistance was a whole 100 gigaohms lower, around 450 gigaohms. While not as drastic as a low-level example, there is still enough error in the unguarded measurement to be unsettling. For very low current measurements, which includes very high resistance measurements, as in the previous example, the signal-to-noise ratio can grow quite small over a rather short cable. A small amount of noise on the cabling tends to produce a pretty ugly signal. The easiest way to eliminate this noise is to move the measurement system closer to the device under test. However, as many of you with probe stations or similar setups can attest to, there is usually not enough room for an average-size instrument right next to the device under test. Nor is there an effective way to mount it there. Hence, we must use a preamplifier module, which can be placed closer to the probe stand, test fixture, or other device. Using a Keithley 4200 preamp with a 4200 SMU allows us to measure down to 1 picoamp range with 0.01 femtoamp range resolution. Now that we've touched on the low-level DC measurements, let's move on to some tips for taking accurate AC capacitive measurements. You need to make 4-wire measurements for AC capacitance tests for much the same reason as for DC tests. Stray impedance in the cables will cause a voltage drop, and our measurements will not be true. However, because there's lots of math going on behind the scenes when applying calibration constants and calculating capacitance measurements can vary wildly with just a bit of error in the cabling. This makes it even more important to compensate for impedance in the line. Keithley CV meters are configured to automatically take 4-wire capacitance measurements, so all you need to do is connect the H-cur terminal to the H-pot terminal and the L-cur terminal to the L-pot terminal as close to the device under test as possible. Many times with capacitance measurements, you will run across measurement errors that cannot be solved by just using 4-wire measurements. This is where cable compensation comes into play. There are 3 types of compensation you can run: open, short, and load. They can be applied in any combination, and if performed correctly, can only improve your measurements. Open compensation is performed with the DUT removed. It is used mostly to compensate for any capacitance in the cabling or test fixture. Short compensation is performed with a jumper in place of the device under test. It is used mostly to compensate for any inductance in the cabling or test fixture. Load compensation is trickier to run as it requires a load which is calibrated over the entire frequency range of the meter. It is performed with this load in place of the DUT and is used to compensate for any nonlinearity or gain in the actual measurements. When selecting cable compensation to be performed during the test, any compensation that is not used will use the ideal value. Ideally, open compensation will be infinite farads. Ideally, short compensation would be 0 farads, and ideally, load compensation would be a 1-to-1 ratio. Here is an example of a plot where we ran a CV sweep on a diode both with and without cable compensation. I only ran open and short compensation, and many times this is all you will need for accurate measurements. As you can see from the graph, without any compensation, our reading was a whole picofarad lower than the correct reading. This equates to about a 45% error in measurement and could lead us to make incorrect assumptions or design decisions with this part. Occasionally, even after trying everything to make a crucial CV measurement, the signal is still noisy. We're using 4-wire connections, we performed open, short, and load compensation, and we have our device under test shielded with an aluminum sheet. What more can we try? It is reality that one measurement terminal can be much noisier than the other in a system. We see this most often with the chuck on probe stations, but there is no reason that it is not true elsewhere as well. This noise is more apparent with capacitance measurements because, 1, we are measuring very tiny currents which are very susceptible to noise, and 2, we source and measure on different terminals, so a seemingly quiet system can have noise that is simply localized near the measurement terminal. Because of the separation of source and measure, many times we can eliminate this noise, or at least quiet it down, by switching the position of H-cur H-pot with L-cur L-pot terminals, thus changing on which terminal the measurement is taking place. In a prober configuration, the probe station chuck is an extremely large capacitor, and it can act as a large antenna that collects random noise. Since the substrate is electrically connected to the prober's noisy ground, the ammeter will be sensitive to this noise and will cause errors in your capacitance measurement. So, the first thing you need to know when making a capacitance measurement is that you should always connect the AC ammeter to the terminal of your device that has the least amount of noise, which generally means the least amount of capacitance to ground. One of the features of Keithley's 4200 CVU is that we can perform this switch in software, so we don't need to switch the physical connections, which could be in tricky places or require extra tools to get the benefits of the least noisy terminal. Let's look at a very simple real-world example. In this example, you have 2 layers of metallization, and you want to measure the interconnect capacitance. Quite possibly, you may not know which terminal has the lowest capacitance to the chuck. Or you might have a wafer chuck that is isolated from ground, which is great for low current measurements, but you still may not know which terminal is most susceptible to noise. Either way, one terminal will be noisier than the other. So, you go ahead and connect your capacitance meter as shown, high terminal to pad 2, and low terminal to pad 1, and you make your measurement. And the capacitance measurement readings are something like the graph shown in purple here. So, it turns out after some experimentation that pad 1 has a capacitance value, chuck value of 5,000 picofarads. So, 5 nanofarads of capacitance, while pad 2 has only 5 picofarads. It is the noise coming from the chuck via the large parasitic capacitance that is causing the measurement error. So, what can you do to correct this? There are several ways, some more convenient than others. First way, you could physically switch the cabling, but that could change any compensation constants that you have set and require those compensation steps to be rerun, and the DC bias would be reversed from where you had it before. Or we could do it, what I consider the easy way, without physically changing anything. Within Keithley's Clarius software, you are able to switch around the AC source, DC bias, and ammeter locations. So, as I just mentioned, in the advanced settings of any CVU test, we can change the terminal of the AC voltage source, the DC voltage source, which is the bias voltage, and the AC ammeter. Setting these options correctly can greatly improve the noise performance of the CVU, resulting in more accurate capacitance measurements. Another feature that comes in handy is the real-time capacitance measurements window. This feature allows us to take measurements as if we had a C-meter on our desk. I use this almost every time I set up a new test, just to make sure that everything is set up correctly and that there are no errors in my setup. We also have a confidence check feature, which allows us to make sure that there isn't too much or too little impedance in the line. Basically, we use a confidence check to make sure that what we think is an open is actually an open, and what we think is a short is actually a short. These 3 features help to eliminate unnecessary troubleshooting steps and make for smoother capacitance measurements in general. Now I'm going to quickly go through some common measurement applications for MOSFET or MOSCAP devices. Some common DC tests are VDS ID sweeps, subthreshold voltage sweeps, and VGS ID sweeps. Some common AC CV tests are a simple CV sweep and a very low frequency CV sweep. When making connections to a FET, I usually tie all 3, or 4 in some cases, pins to separate instruments. This is shown in Figure 1, where each channel has an SMU attached to it. This way, every node is held at a feedback-controlled voltage, and we can measure every current. If there is not an SMU available for each channel, connections can be made as in Figure 2. This configuration is more susceptible to a noisy ground connection and could produce ground loops if long cables are used. Also, the current and voltage at the source terminal cannot be measured. This can result in errors in calculations later on. Everything that we went over earlier still applies here, however. It is important to keep cables short and make 4-wire connections as close to the DUT as possible. Also, guarding and shielding are still important. The VDS ID test consists of sweeping the drain source voltage while holding the gate source voltage constant. This test gives us a family of curves that we are familiar with when talking about MOSFETs. To set up this test, we set up the gate to step from 2 volts to 5 volts with 1 volt steps, which will give us 4 steps. For each gate voltage step, we will sweep the drain voltage from 0 volts to 5 volts. This will give us a good idea of the properties of our device and the characterization we need in order to incorporate it into our designs. This is what the result of the previous test looks like. Notice that we have 4 plots on our graph, and each one corresponds to a different gate source voltage. This image shows very well the 3 phases of FET operation, as well as giving us valuable insight into using it in our own designs. I took this plot using Clarius software and a Keithley 4200A with 4 SMUs as configured 2 slides ago. In a VGS ID test, we hold the gate at a constant voltage with respect to the source, sweep the gate source voltage, and measure the drain current. The blue plot in this image shows very well how a FET can be used as a voltage-controlled current source. Varying the gate voltage while holding the drain voltage constant produces an important characterization curve. This measurement also allows us to graphically calculate the threshold voltage by extrapolating a line tangent to the curve and finding its zero intercept. On the same plot, in red, calculated and plotted out the transconductance and found the maximum transconductance value. The subthreshold slope measurement is an indicator of how fast a FET can turn on and is important for high-speed applications. The process of taking a subthreshold swing measurement is much like the previous VGS ID sweep. It involved setting the drain source voltage to a constant low value, 100 millivolts in this case, and sweeping the gate source voltage from -2 volts to 2 volts. As we are sourcing a low voltage and making a low current measurement, it is very important to use 4-wire measurements and to guard your connections all the way to the device under test. For CV measurements of a FET, we are generally going to tie the drain, source, and bulk terminals together. This effectively makes it a MOSCAP device. There are particular types of measurements where this is not the case, but I will not be touching on those today. You can either solder the terminals together or, as I'll touch on later, use a 4200A CVIV switch, which comes in handy. Connections need to be made from the CV high terminals of the CV meter, that includes H-cur and H-pot terminals, to the gate of the device, and from the CV low terminals of the CV meter, which includes the L-cur and L-pot terminals, to the drain source bulk of the device. After connecting everything, this is the time to perform the cable compensation measurements. First, remove the device and perform an open compensation. Then, place a jumper between where the gate and drain source bulk terminals would be and perform a short compensation. Finally, insert a load in place of the jumper and perform a load compensation. As I mentioned before, all 3 compensations are not required, but can be helpful to reduce noise. Finally, replace the FET and you're on your way to making accurate CV measurements. Performing a simple CV sweep would be one of the more important tests to run on a MOS device right out of the fab. We're going to sweep the bias from -5 volts to 5 volts at 1 megahertz, and we're going to drive a 30 millivolt RMS AC signal on top of that. Measuring the gate bulk voltage and gate capacitance can tell us lots of information about our device, including our oxide thickness and impurity concentration. These, among others, are important results when analyzing a wafer-level semiconductor. Now that we have the CV sweep and a pretty picture of it, it is important to make sure that the data makes sense. Here, we have our results where the oxide capacitance is 4.4 puff and the flat band capacitance is 4.1 puff. This is in line with what we would expect out of similar devices. The flat band voltage can be found by taking a linear interpolation of our capacitance plot, and we have found that it is -1.4 volts. This is slightly more negative than expected, but still within an expected range. From these values, gate oxide thickness can be calculated using the standard parallel plate capacitor equation, and the impurity concentration and Fermi potential can be calculated with further, more complicated equations. Certain device characteristics only exhibit themselves at very low frequencies. To analyze these characteristics, we must run a very low frequency CV sweep, or VLF-CV sweep. This test is generally performed on a test MOSCAP device elsewhere on the wafer and not directly on a MOSFET device. As the name implies, the VLF-CV sweeps over a capacitor at low frequencies. As the maximum frequency of 10 Hz is well within an SMU's performance, we use SMUs to get very tiny current measurements. As with all of these tests, the very low voltages and currents involved require 4-wire measurements, guarding, and shielding in order for accurate results. PreAmplifier modules are also of high importance for this test. You may have noticed during the last few slides that most of the tests I went through required slightly, or not so slightly, different connections to the device under test. We talked earlier about the fact that every time you rewire a test, you change cable constants ever so slightly. This then requires you to rerun any compensations to update the constants you are using, which then slows down the test and just makes for a generally painful process. Then, when, not if, but when, you need to go back and run a previous test, you need to go through all of these steps once again, just for one run of one test. And then you can never get it exactly as you had it before. Enter the 4200A CVIV. The CVIV is a multi-channel switch accessory for the new Keithley 4200A parameter analyzer that allows us to switch between DC and CV measurements while not needing to swap cables at all. Let's look at it a little deeper. So, what can the 4200A CVIV do? At the very base, it's simply a switch between measuring IV and CV on the same device. It eliminates any need to recable, to rerun compensation, and my favorite, we can go back and rerun a test with a different configuration with just a click of a button. It also allows you to measure CV between multiple sets of terminals on the same device without switching their cables, which saves time and cabling. The CVIV switch has 4 output channels and can switch up to 4 SMUs either on or off, one to each channel. It also has 3 1x4 multiplexers for the CV high terminals, CV low terminals, and for the outer shield of the CVU cables. Each CVU channel can switch to any or multiple output channels. Any channel can be switched open as well, which will leave the output floating. The CVIV has 4 SMU inputs, which can be switched on or off, 1 CVU input, which can be multiplexed to any channel. It has of the 4 outputs, and each of the 4 outputs has 5 operating modes. It can operate as passing the SMU signal through, as being a CV high terminal, being a CV low terminal, being a CV guard terminal, which is the outer shell of the CV cables, or it can be an open. For the SMU inputs, each channel can support a preamplifier module or a pass-through module. Either way will allow you to use a SMU on that channel. The preamplifiers will just give you better low current performance, as we described earlier, while the pass-throughs will simply preserve the regular SMU performance. Here are photos of the external connections to the CVIV switch. Notice on the right, the input side, that we have 2 4200 preamps and 2 SMU pass-through modules which fit in the back of the CVIV switch. The CVIV switch is powered and communicates over USB 2.0, and there are some safety ground connections which should be connected for safety purposes. The CVIV switch is 100% software configurable in Keithley Clarius software. There are 2 types of action steps which you use to control the CVIV. One is the CVIV switch, which changes the configuration of the CVIV between tests, and the other one is the CVIV cable compensation step, which allows us to store cable compensation values to be used with each switching configuration, which we have switched using the CVIV switching action. Many semiconductor measurements are made at the wafer level using a prober station. This prober station usually has some kind of patch panel with connectors that do not match the CV meter, which does not match the SMUs. These connectors require different adapters for each configuration and can be, and in my experience usually are, located in hard-to-reach places around the lab. The CVIV is designed as such that you need to make these connections once and forget about them. They just work from then on. As mentioned before when we talked about the preamplifiers, we want our measurement devices to be as close to the device under test as possible. Many times when we're using large probe stations, as shown in the picture, it is difficult to get the measurement devices close, and we must use long cables, which introduces more noise into our system. But the CVIV was designed specially to be mounted directly onto the probe station. In this way, we have our switching high and low CV terminals as close to the DUT as possible. Making connections to the CVIV switch can be very easy. First, we need to connect a CVU, the CV meter, to the 4 SMA terminals in the back of the CVIV switch. Here we'll use an SMA torque wrench. Then we'll connect each SMU using either a 4200 SMU preamp or a pass-through module, which also slides right into the back of the CVIV switch. From the front of the CVIV switch, we'll use 30-inch triaxial cables, and we want to make sure that the cables are smooth and not bent too sharply. And we want to connect the force and sense terminals as close to the device under test as possible. For best results, be sure that the outer shields are shorted together as close to the device as possible as well. While they are shorted together at the CVIV, the closer the better. In summary, for our DC measurements, make sure to use 4-wire connections, guarding, as well as preamplifiers. For CV or AC measurements, we talked about cable compensation, open, short, and load compensation. And these tips can come in handy greatly for MOSFETs or other semiconductor measurements, as well as just general measurements around the lab. We also, finally, we talked about using a Keithley 4200A CVIV multi-switch to switch between IV and CV measurements easily and to simplify prober measurements.
Find out more at Vicom's website.